Hi everyone, welcome to our free body diagram challenge that Shannon has set up. Let me see if I can get my head in here and say hello. We're set up obviously for drawing and not for lecturing, so you're going to hear my voice and not see my face, but that's okay. So I don't know what's to come here, but Shannon's challenging me to draw free body diagrams of some things around the house. So let's go and see where this takes us. Oh, right off the bat, I can't figure out how to advance a slide while recording. What did you do? It didn't work with this.
I used the mouse.
And it's the scroll wheel? Yeah. Okay.
Scroll wheel.
Okay. Here we are. Okay, free body diagram number 1. Dino sitting on a table. So here's Dino's body. There's Dino's big old tail. Dino's face. I'm going to use a convention where I'll use blue for applied loads and red for reactions. Reactions, of course, are the forces that hold in an equilibrium. That's the centroid. That's the center of mass of Dino, which means that we have a load applied. That's Dino's weight. That's one of the forces. Dino is a bit like a bar stool. Oh, right off the bat, I have broken from my convention. Dino's a bar stool. He's held in equilibrium, supported on 3 points, 2 points under the tail and 1 under the, or 2 points under the legs, 1 under the tail. What other loads would Dino be subjected to? Dino is subjected to a wind load. Because I use W for weight, I'm going to use H for wind because it's applied horizontally.
Remember when I say engineers like to just change symbols whenever we feel like it? This is what I'm talking about.
The center of the projected area, which is where the wind load is applied, is not necessarily the center of mass. So I've got 2 different centroids. I've got the center of mass of Dino for his weight, and I've got the center of the projected area, which is where the wind is applied. So what happens under wind? Well, the wind generates overturning and generates shear. So we're the shear component is resisted by friction at the base, which balances the horizontal component. Then there's also an overturning component. So I'm just going to dot in the overturning. This isn't an additional force, it's the effect of the wind being applied eccentric relative to the point of resistance. And that winds up being resisted this way. So we have 2 reactions here on the legs pushing up. We have 1 reaction pushing down on the tail. Now, you may ask a very smart question, which is, he's not stuck to the table. How can we have a pull-down reaction? Well, we have a pull-down reaction that's balanced by the weight. So the net of these, we can put a little plus sign here, meaning that we can superimpose those loads. The net load on the tail is going to be, has to be acting up because we're in compression, but it's a very small force. If the wind load was high enough that this was a negative force, then he would actually topple over. So there's the 3D free body diagram of Dino himself. That's the last time I'm going to do Dino, because I realized that the point wasn't to look at Dino. The point was to consider Dino a load and look at the impact on other things. So what are the things that we're going to look at? This is our table. And this is Dino sitting on our table. There are a few things that we need to incorporate into our table free body diagram in order to demonstrate that it's stable. One thing we need to recognize, I'm just collapsing this into 2 dimensions because it's more meaningful in 2 dimensions. The 3D is not, doesn't really add a lot of information. So we're going to indicate here that we have a load coming down. That's Dino. We're going to apply a pin support here. We use this little symbol for a pin support. Often I'll eliminate the hatching. And on this side, we're going to put a roller support. The reason we put a roller support here is to avoid unintended load paths. So this is often how we would model a frame like this. So what are the forces that we need to hold it in equilibrium? Well, Dino himself will be balanced by 2 vertical loads. Recall that we had the potential to have wind on Dino, like this. How does that get resisted? Well, we have called this a pin and roller, which means that the horizontal load can only be resisted at the pin. We do this not because it reflects reality, but because it makes it statically determinate. Statically determinate means that we can figure out where all the forces go. We don't need to know relative stiffnesses of things to figure out where all forces go. The reality of this, of course, is more like this. We would make the very reasonable assumption, let's call this W and this H. We would make the very reasonable assumption that this force is H over 2, this force is H over 2, this is W over 2, this is W over 2. So we've simplified our problem here. We've squashed it into 2 dimensions. So this represents a pair of legs because that's meaningful to us, and it's a simplification that allows us to deal with it. And the other thing we've done is we've made our problem determinate by saying that these 2 are equal. And now we can solve the problem. So here's a different version of the problem. Let's see what this looks like. So now we have our table. I'm going to put a pin, and we're going to use our equal reactions assumption to represent, because it's more representative of reality. Now we've got Dino lying on his back. In this case, Dino's load we can represent as a uniformly distributed load. The load is being spread across the table. This is a slightly different condition than the point load in the middle. The reactions wind up being exactly the same, whether Dino is sitting up or lying on his back, the reactions are the same, W over 2, because we've put Dino in the middle of the table. From a wind load point of view, his center of projected area is lower, so the wind load is lower, but the impact of the wind load is the same. H over 2, H over 2. And here we're pulling down on this leg and pushing up on this leg. But of course we can't pull down on this leg. The net effect of these two, if we add that arrow and that arrow, we wind up with a little arrow here and a big arrow here. Because if that one reverses direction, that means that the table is tipping over. So we're not looking at, I'm not going to try and quantify these except for, the very, very simple things, H over 2, W over 2. But you can see the difference between Dino lying down on the table and Dino standing up on the table is really the difference between a point load and a uniformly distributed load at mid-span. If you remember your free body diagrams, or your beam diagrams, really the meaningful thing here is that the bending moment diagram in this case looks like this. Superimpose the bending moment diagram on the table versus this. Okay, let's see what else Shannon's got in store. These have been easy for us so far. Number 3. Our table. Our pin supports. Now we have Dino sitting right here on the corner. So the reactions, well, Dino is sitting right here on the corner. And so for equilibrium, 100% of his load, this is actually something quite interesting, that the resultant of the load has to pass through the applied load. So in this case, up here, I'm going to dash in the resultant. The resultant is the sum of all the reactions applied at the centroid of the reactions, and the resultant has to line up with the applied load. In this case, the resultant lines up with the applied load. So we have W, there's our weight. We have W as a reaction, equal in magnitude, lining up through the applied load, and we have nothing on this side at all. Now, just for fun, I'm going to apply our wind load here. H. Well, our reaction to H over 2, H over 2. Now let's look at the vertical reaction that we need to hold in an equilibrium, because remember that H is generating overturning, and we need to resist that overturning. It has to go in the opposite direction. So we have our H is this way. We need a reaction that goes the other way. So obviously we need to superimpose these. Let's add that reaction to this reaction. We wind up with big equals pull down. Can't have that. We're not stuck to the ground here. So what that's telling us is that this is an impossible situation. If Dino is sitting right on the corner and we apply a lateral load this way, we have a stability failure. We're going to tip the table over. And that it checks out intuitively, right? But does it? would we tip the table over? If we push on Dino at the top of the table, would we expect the table to turn over? The answer to that is no. We would not expect the table to turn over. There must be something we're missing. And in fact, there is. We have neglected the weight of the table. So in fact, we wouldn't tip over until we exceed the weight of the table. So I've been doing these diagrams in an overly simplified way, implying that the table is weightless. But of course, the table is not weightless, and so the table will act as ballast and keep us from rolling over up to a certain point. Okay, let's look at a Dino sitting on a chair. Nice little diagram of our chair in 2 dimensions. We're just going to look at the 2 important dimensions. We have Dino sitting here. This is going to be familiar to you. We're going to put pin supports down here. We've got Dino's weight. We have a horizontal load here of wind. We have the weight component of our reaction distributed equally between the pair of legs, or the pair of pairs of legs, of course. And then we also have so this is W over 2, W over 2, H over 2, H over 2. Now, what's missing? What's missing, of course, is that while we've dealt with our translations, we can't slide because we have resisted the horizontal force. We're not going to drop into the middle of the earth because we've resisted our vertical force. We haven't got what it takes to keep us rotating. So what we need to keep us from rotating is a couple that looks like this. I'm going to just for fun, I'm going to call this, well, I'm not going to bother. I'm so tempted to get into the math all the time. So this is the couple that we need to resist the overturning. We can add those, we go equals, and we wind up with a net reaction that looks like this. Very small on this side, much larger on this side because the wind is blowing that way. If the wind was blowing this way, we'd have a large reaction on this side and a small reaction on that side. So this looks just like it did for the table. And in fact, we can draw our bending moment diagram superimposed on the horizontal surface, and you'll see it looks just like the one that we did for the table. Okay, Shannon, you made it easy so far. And easy stops. So what happens when Dino is farting around like my son Duncan, hanging on the back of his chair? He's going to break both his elbows like Ty Tennis did. Here we have Dino hanging on the back of the chair by his chin. What's going on here? Well, remember where our center of mass is. Our center of mass right there. So there is weight. Our center of wind, center of projected area, right here. Just for fun, I'm going to orient the wind this way this time, because that's the worst way. This is one thing that is worth pointing out. When we're doing engineering, we always try to guess at the worst case. You know, the wind can blow from any direction, including up and down. And what we want to do, so we could, in theory, evaluate an infinite number of load cases. because the wind can blow from any direction. But we can apply some engineering judgment and determine which way is the worst case. And what we know is that because the load is hanging out here, it's going to be worse when the wind blows this way. So that's the one that we're going to look at. So let's look at what's going on here. Well, we've got weight. The weight is applied out here. We know that the resultant has to pass through that. Well, how does it pass through that if it's not in between the two legs? If you add those up, your resultant is going to be out here. You can take my word for it, but that is the resultant of that as a couple. That is problematic for us. It's problematic for us because we know that we haven't anchored down our chair. Our chair is not actually stuck to the floor. But let's look at this. We're missing a component here. We've got Dino's weight. We don't have the weight of the chair. When we add the weight of the chair in here, we wind up with this. Add those, equals, we wind up with a very small reaction here, equals a big reaction here. So far so good. We've got a little reaction here and a big reaction here. So this is W from Dino, this is W from chair, this is the net. What happens when the wind blows now? Well, when the wind blows, we have a vertical reaction pushing up here. We have a downward reaction pulling down here because the wind is creating a couple like this. Of course, we're resisting sliding here. The net reaction and you can see we have a problem. So when Dino is hanging off the back of the chair, we're in a very tenuous situation. We're fine as long as the chair is heavy enough to resist his overturning. As soon as it's not, then the chair tips over and it can't really resist any wind. So when Duncan is hanging on the back of the chair there, totally fine. As long as Dad's here working on his computer. But as soon as Dad stands up, Duncan's chair tips over because I am contributing the ballast to the chair to keep it from rolling over. Because this is an interesting one, I think it's worth drawing the free body diagram of Dino as well. So I'm just going to slide this down out of the way here. Let's look at what's holding Dino himself in equilibrium. There's Dino's weight. Well, we know that he's, what's holding him up? He's hanging on by his chin. That's what's holding him up. What we can see now is that we've got this tendency to rotate this way. So what is preventing that rotation? What's preventing that rotation is a horizontal couple. His knees are bearing on the chair and his chin is bearing on the chair. And that's what's resisting the horizontal couple. So let's add up the forces here. Vertical, vertical, it's in a vertical equilibrium because the vertical reaction equals the vertical weight. So we're good there. Horizontal, horizontal. Horizontal force here equals the horizontal force there. The pull on his chin equals the bearing on his knees. And so we're in horizontal equilibrium. This eccentricity is tending to cause it to rotate. That is being balanced by a pull here and a push here, which tends to make it rotate the other way. So here's a diagram of Dino in static equilibrium. So you wonder, you say, okay, but does that have any application in the real world? Well, it sure does. Let's look at a situation where we've got someone climbing a ladder, a vertical ladder. What are the loads on this? So we're going to have a So we have someone climbing a vertical ladder. The applied load, of course, is here. That's the weight of the person. We know that all of the vertical gravity load is borne on the feet. The arms don't carry vertical load. At least if you're climbing a ladder properly, they don't. This results in an eccentricity. Okay, often we'll do this. If I want to highlight the eccentricity that's causing rotation, I'll do this. And I'll put a rotation arrow. So the weight is eccentric. So what resists that tendency to rotate? Well, the arms are pulling and the legs are pushing. And so now we're in equilibrium. So what's holding the person on the ladder is exactly the same phenomena that's holding Dino on the back of the chair here. The really vulnerable thing here, right here, how much can Dino hold his chin down to hang on to the back of the chair? Here, at least, we've got hands that can grip onto the rung of a ladder. Okay, Shannon, these are getting more interesting. Thank you. Okay, this is another fun one with a very real-world application. Here we have our chair. Here we have Dino.
Oh my goodness, are you still on Dino?
Yeah, for sure, but I'm having a totally good time. And the more importantly, they're having a good time, Shannon.
Well, that's the important thing. To have fun.
There's Dino leaning on the chair, even though I haven't made it look like, here, I'll extend an arm out, make it look, I'll give him a big
Remember the camp,
shoulder.
the light, I don't have a dimmer and it's sunnier than I thought, so just make your lines dark.
Oh, I see, okay. So, there's Dino leaning on the chair. Here we've got weight. The interesting thing about this is we have to solve Dino in order to solve the chair. We have weight. Yeah, I've really drawn this wrong. Let's draw the ground like. Okay, I'm going to do this again because the way I've drawn it is very misleading. As wonderfully graphic as it was, it is quite misleading. So, I'm going to really tip Dino over. I'm going to have him lean on his head. Okay, here we have it. There's Dino leaning on the chair. We have to solve Dino first. Center of mass. There is our weight. He's leaning, so this foot is up in the air. There's our shadows. Those are shadows. Beautifully rendered shadows. His weight is being borne on his foot. It's eccentric. which is tending to make it want to rotate. So what is preventing the rotation? We have a horizontal couple like this. Now, you can see that there's some simplifications that I'm constantly making. I'm assuming that there is no friction here, that we don't have a vertical reaction when we're leaning. In fact, there would be a little bit of friction, but it's small. And what we do as engineers is we take a philosophy that if it helps, ignore it. If it hurts, include it. This tiny little bit of friction is helpful, but it's hard to quantify, and we know that if we ignore it, we're going to have a safer solution. So we're going to ignore that little bit of friction there. We're going to assume that it's a frictionless surface, so it can only bear horizontally. And there's our free body diagram. Vertical reaction, eccentric from the weight, and the rotation is born. The rotation is resolved as a horizontal couple between the feet and the head. Now, here is the challenge with this. This is friction equals mu W, where mu is the coefficient of friction, and you're not out of line to say it's around 0.25. That's a reasonable range. It could be up to 1. It's never more than 1. Well, no, I guess it could be sticky. It could be more than 1. It could be up to 1. It could be as low as 1%. But if we say it's 0.25, what that means, that limits this angle. And we know that if he gets too far down, his feet are going to slip out. Another very real world situation here. This is our ladder problem. We have our ladder. We have someone climbing the ladder. So we have weight. We have vertical reaction, horizontal reaction, horizontal reaction. First of all, the way I've drawn it here is really problematic because, all right, we're eccentric this way. This guy is going to tip over backwards. But even as he gets up the ladder, or even if he adjusts his stance, let's adjust our stance so that we're really close. And you've all seen people climb ladders this way probably. Adjust your stance so that you're really close. The friction here is critical. We've got to make sure we have enough friction at the base to keep the ladder from kicking out, which is often why we have a pal standing there holding the base of the ladder to make it kick out. It's also the reason why we don't climb ladders at angles like this. You need your ladder to be at a relatively steep angle. The rule of thumb is you need your ladder to be as steep as it can be while still allowing you to have your center of gravity inside of your the base of the ladder. Okay, moving on. There are two things that we can talk about here. One is the tree. How does the tree work? Well, let's look at it. We've got weight. We have a horizontal force. We could simply draw this free body diagram. We could represent the tree as a stick. And put a fixed base condition here. And represent W H, and M. So if we ignore what's happening below grade for the tree, this is what we get. We have moment resistance at the base of the trunk. We have a horizontal force at the ground plane, taking out the shear, and we have vertical reaction at the ground plane, taking out the resisting the weight. If we want to look a little further at it, we have our tree. And we have a root ball. We know that this is full of roots, but the roots all engage soil, and we have a root ball. And the root ball keeps the whole thing in equilibrium. So we have horizontal load due to wind, we have a vertical load due to weight. And now what's going on down here? Well, the weight, its own weight, doesn't really help us if we are resisting, if our resistance is all here in the center. So if we have a big heavy thing sitting on a point, it's just going to tip over. So that's the way a tree is, right? Unless we imply a moment connection. So what's actually happening here? Well, we have the weight of our root ball as well. And under lateral load, we wind up with reaction here, the horizontal reaction here, and because this is large, we can actually develop a couple across the width of the root ball. So I'm representing it with a force. I'm representing it with as a couple because it's interesting to think about it this way, but this is effectively what's happening. We're resisting our vertical load, we have some pull out, we have some pull down, and if we take the resultant of those things, I'm going to represent the resultant in green. What we wind up with is the resultant somewhere here in the root ball. If the resultant winds up outside of the root ball, we're in trouble, we're toppling over, and that's what happens in a hurricane. But because the root ball is large, we actually can have our resultant doesn't have to lie straight in the middle of the root ball. It moves over so that we can resist overturning loads.
Can I steal? Thank you.
Here's the other interesting thing that's in this one, is we have a swing.
Try not to go too longer than an hour.
Okay.
Actually, you know what? They can watch as much as they want or not watch.
Yeah. We have a swing.
It's about testing. It's about
Weight.
knowledge.
So right here's our reaction now, pin reaction. Weight. Our free body diagram is complete. The reason that the free body diagram is complete is because the swing is stable and flexible and will always rotate to bring the center of gravity under the directly under the point of support. So this is always the equilibrium condition for a swing. We can try and draw the swing this way. Put the weight here. And the question will be, well, what holds it in equilibrium? The answer, what holds it in equilibrium if you don't have this couple? And the answer is you don't have that couple, so it's not in equilibrium and it's going to swing down into equilibrium and be vertical. Now, how did we get it here? Well, Dad came out and pushed on it. And so now we have a horizontal couple there. As long as Dad's here to push on it, we have a horizontal force, and we can hold it in equilibrium at this rotated position. But because it's a swing, as soon as we let go, it's always going to align the center of gravity directly under the point of support, so that the resultant's lined up. Okay, so let's have a look at this lovely light fixture. This is one of those situations where we'll challenge you to draw a free body diagram, and there's too many pieces in this, and so we can actually wind up confused trying to draw this free body diagram. But let's do it anyway. We have a chain draping here, so we have one weight. We have the weight of a fixture here. We have the weight of a fixture here. So I'm going to call these 1, W2, W3. We have 2 anchor points. I guess I could have given my beautiful symbol for anchor points. We have 2 anchor points. So this is fairly easy. We're going to call this reaction W1 plus W2 over 2, and this one is W3 plus W2 over 2. So we've kind of solved this, right? We haven't really. These guys will align themselves so that the center of reaction is directly under the support. So that part is good. This chain, though, this guy has no flexural stiffness. So let's look at what it takes to hold that chain. This is what we call a catenary. I'm going to do a little breakaway diagram here and show a catenary. Load uniformly distributed along its length. It has no ability to span. And so the catenary reactions have to be this. And we know this, right? We take a piece of chain and we hold it in the air and it'll drape in between, but it wants to pull our fingers together. So there is another component of force here. In order for that catenary to be held in equilibrium, we also need a pair of horizontal forces here. Okay. Baby gate. This is an interesting one. We are going to break this problem down into, this thing is on a hinge, but the gate itself doesn't care whether it's in an open or closed position. It matters not a bit. So where it sits on the hinge doesn't matter to the gate. So in a way, that's what we call a red herring. We throw that in there just to confuse you. The fact that it's on a hinge makes it seem like it's important. The fact that it's on a hinge, in fact, is not important at all. So here is our baby gate. We have 2 hinges. We have one here. We have one here. Let's look at the forces on this thing. we have our center of weight is right here. Now, this is a statically indeterminate problem. How is that force distributed between that pair of hinges? Well, what we do is we simplify our problem by saying these hinges look the same, so we'll assume, oh, well, this is a door. We're going to do a door first, then we're going to come back to the baby gate because I drew it wrong. I wasn't paying attention. So we are going to make the reasonable assumption that the load is borne equally between the two. Okay, so what we can see though is we have this residual eccentricity, that the center of load down is not aligned with the center of resistance up, which is tending to make it want to rotate. By the way, the magnitude of the force trying to make it rotate, the moment, is equal to W times E. The weight times that eccentricity is the magnitude of the rotating force. So that is not an equilibrium. We've got the vertical component taken care of. We have no external horizontal load on it. We could, but it's trivial. So what holds it in equilibrium? We need a couple on the hinges. So when you have a door, always the upper hinges are trying to pull out of the wall, where the bottom hinges are trying to push into the wall. So now let's look at a baby gate instead of a door, because I screwed up. Baby gate hinges are not quite the same. The baby gate only bears load on the bottom hinge, which does not really change things all that much for us. It just says, I didn't draw the hinges in here, I'll draw them. This is a pin roller condition. So the upper hinge is called, or is modeled as a roller. It carries no vertical load. The lower hinge carries all the vertical load, weight. So we have weight, we have weight. You can see that once again we have eccentricity, which results in a moment, a tendency to rotate. What's that resisted by? Well, it's resisted by a horizontal couple. It's pushing into the wall on the bottom, pulling away from the wall on the top. By the way, actually, here I am saying it's pulling away from the wall, and yet I've drawn the arrow this way. I'm drawing the reaction. I'm drawing the force that it needs, that the wall is imposing on the gate, not the force that the gate is imposing on the wall. Because this is a free body diagram of the gate, not a free body diagram of the wall. So this arrow is representing what the wall is doing to the gate, and that'll always be the case. If you start mixing those things up, and a lot of people do, and they get themselves very confused that way. But if this arrow represents what's happening to the wall, then you're going to find that the things don't add up. When you add up your horizontal arrows, you wind up with, or the vertical arrows, you wind up out of equilibrium. So what we want to do is we want to show that when you add that arrow to that arrow, you get zero, because that is the definition of equilibrium. So this vertical load here is pointing up because the wall is pushing up on the gate, and this is a free body diagram of the gate. For sure, the gate is pushing down on the wall, but we're not drawing the diagram of the wall, we're drawing the diagram of the gate. Okay, this is an interesting one. Here we have C-shaped coffee table. We have a glass of water here, weight of H2O, and we have weight here, the weight of the coffee table itself. And we have some, we know that it sits on uniformly on the floor. It bears on the floor. And in fact, actually, I should have said, I've drawn this wrong. The center of mass of this thing is back here. There's our weight. So we've got a glass of water here. We have the weight of the coffee table here. And just for the purpose of illustration, I'm going to move the glass of water over here. So I'm going to redraw this for you. With the moved glass of water. Okay, so what's holding this in equilibrium? This would have wind on it, but in a way that's not so relevant. But the interesting part is the weight. What do we know about the bearing here? Well, we know that it's got some force. It's sitting on the ground. It's not tipped up. It doesn't have four legs. It has some force all over the ground. Or all over the base. We need to make some reasonable assumptions. One of the assumptions we're going to make is that it's a straight line. The difference here, I'm going to just draw, this is a distributed reaction. We're going to make the reasonable assumption that this is linear. That the amount of bearing stress is proportional to the distance along the length of the base. And this is the kind of assumption that is made all the time. It's a very reasonable assumption. It is not necessarily perfectly accurate, but it's very reasonable. Okay, so we've got this. We know that the resultant of this distributed force has to equal weight plus the weight of the H2O, the weight of the glass of water. We need to figure out where is the resultant of those two. And then we know the resultant of those two is going to be somewhere in between there. So this, it is helpful for us to draw the result. I'm going to draw the resultant in green so it's not considered to be another load. That when we add that vector and that vector together, we wind up with a resultant that is somewhere in between them and that is equal to the sum of the force, W plus WH2O. So that is what we're trying to resist. We know that the reaction has to line up with the resultant. I'm going to call this reaction. So we know our reaction resultant has to line up with the resultant applied force. And so what we have is an uneven bearing distribution that has to have its resultant lining up with that force. Now, we're not going to talk about how to calculate that. I'll show you a few simple examples. If we have uniform bearing distribution, the resultant is equal. If we have a triangular bearing distribution, the resultant is at the 1/3 point. which means that if we have a trapezoidal bearing distribution like this, our resultant is bounded between the middle point and the 1/3 point. The resultant has to be in there for a trapezoidal bearing distribution. So what we do is we can use some relatively simple math to figure out what is the trapezoidal or triangular bearing distribution that gives us the resultant that lines up with the reaction. And why would we do that? Well, the reason we would do that is because this bearing stress is interesting to us. That symbol is sigma. Sigma is a circle with a little curvy cap on it. This bearing stress is interesting to us. It's not interesting to us if it's a table sitting on a floor, because the floor will have lots of capacity. But I don't know if you guys will recognize this. As a building, this was the Fung Lok Choi Temple. I'm not sure that it's called that anymore. I'd have to look it up. But this is a project with Shim Sutcliffe. Tai Chi Temple. Look it up. It is extraordinary. And we worked on it with them. And this is the massing of the building. There is the weight of the building. And below ground, we had a footing that looked like this underground, so that our reaction, our resultant reaction, lined up under the building. And we have a trapezoidal bearing stress under our big giant footing. And we had to make sure that the bearing stress at the tip of the footing did not exceed the bearing capacity of the soil. So, very real world example of exactly that problem. Okay, this is an interesting table, and I am not sure. This actually may be a little too complicated to get into. And when I say it's too complicated, what I really mean is that I'm liable to make a mistake somewhere along here. But let's look at it in the simple direction first. There's our table in the simple direction. We have weight, we have wind, horizontal force. The simple part, we know the horizontal force is resisted by friction under the legs, so that's fine. We know that the weight we can represent with a resultant here. That's a resultant because that's not a discrete point, but we know that the weight has to get resisted by a resultant underneath the weight. We know that the wind is eccentric, which tends to create some overturning this way, which means that the wind gets resisted by a couple, like that, Okay, so let's look at what this does to us. Let's find the resultant of those three things, this plus this plus this. Redraw the bottom. What we wind up with is a resultant out here somewhere. Is our resultant. But it's not point loads. We don't just bear on discrete points. We bear continuously along the surface. And so what we wind up with here is a distributed bearing condition. And just because I've said of where I drew the resultant, I know that it's triangular and follows this 1/3, 2/3 relationship. So I figure out where the resultant is, and then I can tell of those three conditions. Remember, I drew those three conditions. We have the box condition where it's in the middle, triangular condition where it's at the 1/3, 2/3, and we have the trapezoidal condition where it's somewhere in between. I calculate where the resultant lies, and then I know whether it's that condition or that condition or that condition based on where the resultant lies. And if the resultant is out here, our table is toppling over. Okay, so that's the simple one. That's the simple direction. Let's look at the complicated direction, because this is often confusing to people. Okay, so what is the part here that's confusing? As soon as anybody draws triangles, we have an inclination to think it's a truss, and to think that because it's triangulated, there's no bending moment. Because we're taught with trusses, you triangulate your truss and then you don't have any bending moments, and that's what makes it effective. And so people draw an X and they say, triangles, it's a truss, I don't have any bending moment. But in fact, this is not triangles, it's an X, and this thing behaves quite differently. We can see though, like, let's ignore wind on this thing. W over 2, W over 2. The free body diagram of the overall structure is actually very simple. But let's look at the free body diagram of one leg. Well, we know that is W over 2. We know we have a force coming down from the table, and if we break it apart, we look at the table independently. We have W over 2, W over 2. It has to be. So this has to be equal to W over 2. So we've got a leg sitting there. And we have a force coming in here, force coming in there. They're eccentric. The leg wants to rotate that way. What stops it from rotating? Well, we have a pin here. So possibly there's a force that can get transferred. What we know is that the force on one leg has to be equal and opposite to the force on the other. And you're just going to have to take my word for it. That means that we can't have a vertical force. Because if we have a vertical force up on this leg, we need to have a vertical force down on the other leg, and we're no longer in equilibrium. We're not balanced. So we can only have a horizontal force on this. So what we wind up with in this diagram, we know that the reactions are tending to make it rotate this way. We need forces to make it rotate the other way. And those forces exist here and here. So we draw the diagram of the other leg, of course. I'm just going to draw it superimposed. Well, I can't draw it superimposed very easily. I'll draw it over here. If we draw the other leg, it's just the mirror image. And we know that it has to be the mirror image of that free body diagram. We know that we can't take a horizontal force out at the base. If we could, that would be fine, but we can't. We'll treat the base as frictionless. Even though it has friction for wind, we treat it as frictionless for gravity. So this is our diagram here. Okay, so what does that mean? Well, let's take this force. We know that this force has a component parallel and perpendicular. And this force has a component perpendicular and parallel. What that means is that this section of the leg has a little bit of extra compression in it, and we have a component of force pushing perpendicular to the leg, which means we have bending in this leg. This is where I was going with this. An X-frame is a bending system. It's not a truss. It's things working in bending. And it looks like a truss just because it's triangles. There's a number of analogies here. As soon as we draw an arch, as soon as we draw a shape like this, people think it's an arch and assume that things are in compression. But the fact is that if we have a roller situation on this side and a fixed situation on this side, this is just a beam. It just looks like an arch. This is one of those situations. It looks like a truss because it's triangles, but in fact, it's a bending system. Okay, that was a complicated one. We'll make sure that's on the exam. So go back and study that particular problem. I'm only kidding. Okay, this is a cantilevered guard. Very simple. We'll ignore weight. Oops. Applied load is blue. Reaction is red. We have eccentricity, and eccentricity that tends to want to make it rotate this way, which means we need moment. So we have H, M. M equals H times E. I should have said that this is a moment connection. Okay, very simple. Let's see what's actually happening here. Let's drill down a little bit. What we have is a shoe connected to our deck. We have a horizontal force. We have two little horizontal reactions at our pairs of screws. And we have a couple. So I've drawn it too small for you to tell what I'm drawing here. So let's redraw this, put a break line. We have our horizontal force at the top. This is our base, blown up to 3 times its real scale. We have friction here, or we have, sorry, screw shear here, H over 2, H over 2. We have a screw in pull out, and we have compression here. So this is that screw working in tension. So we've got screws into the deck that are holding it down. Now what's happening here? Well, engineers often consider this to be a couple, and they say, oh, well, the other screws take the other component of force. You get down on this screw and up on this screw. It's not totally unreasonable to do that. But the fact is, what we've got here is we have a piece of molded plastic with a hole in it. And we have a screw, countersunk screw in this hole. This screw can work in pull-out, but it can't work in compression. There's no way for this to work in compression. If this piece of molded plastic is moving down, or tries to push down, it's just going to slide in that hole. There's nothing to stop this plastic from moving down relative to that screw. So what is going on? Well, this is the diagram of the plastic now. We have reaction here from that screw. Here, we have some distribution of bearing stress against the wood. The screw isn't carrying the compression, it's bearing against the wood. So the reason it's not unreasonable to consider the screw to carry it in compression is that it's not unreasonable to represent that bearing against the wood as a triangular stress distribution with its centroid along the screw is not an unreasonable assumption. The fact is that reality, if this is our base and this is our screw, reality might be this at one end of the spectrum. And it might be this at the other end of the spectrum. So the center of reaction for that bearing might be right at the very, very tip of the plastic, or it might be distributed through the whole compression zone from the middle of the screw to the compression side. And we don't know where it actually is. That would be an extraordinarily complex problem. So to put it at the middle of the screw is a reasonable thing. The conservative thing from the point of view of pullout is to use this one, because this is the one that will have the smallest resisting arm. This eccentricity here you can see that's the smallest eccentricity, that's the biggest one. The amount of pullout force is inversely proportional to that eccentricity. So the larger the eccentricity, the smaller the pullout force. So this is the conservative one, but this is not unreasonable, and it's very simple. Okay, cantilevered hearth. Well, we're not going to show you. I'm not going to show you how we built the deck. So we're just going to draw the hearth. We're going to put a big old weight from the fireplace, and I'm going to tell you that it is fixed here. That is a fixed joint right there. So here we have weight. The vertical load has to get resisted here because we have nothing back in there. So what resists the overturning? Due to this eccentricity, has to be a moment. So that is just a very simple cantilever problem. We have weight, we have resistance, and we have a moment that takes the eccentricity, that resists the eccentricity. And we're saying what happens back here, somebody else's business problem. We always have to do that. Eventually we have to stop and we say, at this point we're considering the structure to be okay. Generally it's when we get to the earth. When we get to the earth we say we're good. What happens in the middle of the earth is God's problem. Okay, this is an interesting one. I think I know where Shannon's going with this. It's a slide problem. We have a kid sitting on a slide. We have weight. We have two reactions, and we're going to neglect lateral loads for the time being. This is a very simple problem. This is one of those ones, though, where the slide looks kind of like an arch, right? But we have to consider that this slide, we have to consider the surface to be frictionless, so that the slide, and it's virtually weightless. The slide doesn't weigh anything. So this can't work like an arch. It has to work like a beam. The structural behavior of this, notwithstanding the triangle, is a beam. And if it breaks here, it's just going to go flat. The integrity of that joint is what controls the integrity of the slide. It's not behaving as an arch, it's behaving as a beam. Okay, so that's fairly simple. I would say, actually, let's redraw this just for the purpose of completing the illustration. Here's our slide. Let's disconnect it right here at that joint. Well, I've already told you if you disconnect it at that joint, it's going to collapse like this. But then let's get big old dad to stand here. Dad's big old pal to stand here. And now what happens? Now we apply weight here. We have a vertical reaction here, vertical reaction here, a horizontal reaction here, a horizontal reaction here. And even though it's broken there, it's not going to collapse. So in its normal state, it relies on the integrity of this joint. If we can resist outward thrust at the base, the load diagram changes and it becomes an arch. We try and avoid load path diagrams because they are not mathematically rigorous, but the load path diagram would be this. Okay, so there's our slide. Now let's look at a slide with a kid in the middle. The challenge here is that this is a statics course on structures. And this is a statics course on structures. We take for granted equilibrium. That is the basis of everything we do. We are not thinking about a kid sliding down a slide. We are putting a kid here. Now this is a slide, which means that the slide is a frictionless surface, which means that the only force that can exert between the kid and the slide This is a maybe I'm going to draw the kid. Here's a kid sitting on the slide. There is no friction between the kid and the slide, so we have to solve the kid diagram first. And what we know is that this can happen that this is not statically determinate. If there was a kid here on the slide, he would be sliding down unless he sticks his legs out like that and stops himself. So for the kid to be halfway down the slide, he's got to stick his legs out like this to stop himself from sliding. Let's draw the diagram of the kid. I'm going to use green because I've already screwed this up and I don't want to draw it again. Diagram of kid. Weight. Reaction from the slide has to be at 90 degrees to the slide surface. It has to be because it's frictionless. It's a slide. Reaction from the slide has to be that way, which means we have a reaction at the base like this. And when we add up the horizontal and the vertical reactions at the feet, plus the diagonal reaction at the slide, plus the weight, they have to add up to be 0 to hold in equilibrium. So the interesting thing here is that for this to be static, come back to our slide. What we know, we don't have a weight bearing down vertically. We have a weight at 90 degrees to the slide. We have two vertical reactions here, one bigger than the other, I guess because the weight is kind of closer to that end. This one is going to be bigger. I'm just going to break this up. I'm going to show you that this we can represent with a vertical and a horizontal component. We can always represent our angled forces with a vertical and a horizontal component. And that helps us add things up and solve diagrams. So our weight is coming in at an angle, has a vertical component, a horizontal component. The vertical component, we split between these two. Where does the horizontal component go? Well, if it's in equilibrium, that horizontal component has to get divided between these two legs. So even without the wind blowing on it, in this condition, we have a horizontal component. So let's think about what you think is actually going to happen in this condition. You are not wrong to think probably what's going to happen is that the slide is going to squeeze out like a bar of soap. And that's probably what would happen. Very little friction down here, which means that we will very quickly overcome this horizontal resistance due to friction, which means that we are no longer in equilibrium and the slide is going to move over. So when someone is sitting halfway down the slide trying to hold themselves there with their feet on the ground, the slide is probably going to slide back. Okay, trampoline. Trampoline is a catenary problem. I'm going to just draw the very simple thing right in the middle. We're going to take a 2D section through our trampoline. I'm going to forget what's happening at the frame. Here's our frame. Here's our trampoline. We're fixed in space, one end and the other. and we have weight. Now, I have been drawing external free body diagrams. If you draw this, you're not wrong. But Shannon talked about method of sections before, and the method of sections, the basis for it is that if an element is in equilibrium, then every part of it must also be necessarily in equilibrium, which means you can cut it anywhere and it has to be in equilibrium. Let's cut our trampoline and say we're only going to look at this side. W over 2. We got half our load going to one side, half going to the other, so this is W over 2. So what's going on here? We have eccentricity, tending to make it want to rotate. What holds this in equilibrium? Well, if this was a beam, we would have a moment. That's the bending moment in our beam. So now this is in equilibrium. We got our vertical components taken care of. There are no horizontal components, and we have bending moment. So the tendency to rotate this way due to the external applied loads are balanced by a bending moment in the other direction, and that's in equilibrium. That's our method of sections for a beam. What happens with a trampoline when moment equals 0? We are not in equilibrium. And this is what we call a shape active structure. Basically, it relies on changing shape in order to be in equilibrium. So let's look at this. Here's my horizontal datum line. When we step on a trampoline, it sags in response to our load. It may not sag very much visually, but it sags. We have a horizontal force and a horizontal force. So this is our forcing arm, our eccentricity of load. This is our eccentricity of resistance. And this horizontal force has to be large enough to hold it in equilibrium. Now what we know is that the rotation is a product of force and eccentricity. The larger the eccentricity, the larger the tendency to rotate. And what we know is that your trampoline stays pretty darn flat when you stand on it, which means that this eccentricity is much less than this eccentricity. And what we know from that then is that our horizontal force is much greater than our vertical force. So this is a fairly standard catenary type problem. And the thing to bear in mind is that if the vertical load is resisted by a catenary, the horizontal forces are much larger than that vertical load. They might be 10 times as high. And this always catches architects and engineers by surprise. They say, you know, it happens with banners, for example, under wind load, or people are always looking at, I mean, fabric structures, covered structures. People look at the weight of the structure and therefore assume that the forces are small. But in fact, the in-plane forces are very large, much, much larger than the weight. So we have very large in-plane forces. Now, we've only drawn a section through it as though it's a two-dimensional problem. Of course, a trampoline is a three-dimensional problem. right? There's your frame. Well, what we know is that we have all of these forces pulling in. I'm drawing the free body diagram now of the frame. And so that horizontal force is now my applied load. The horizontal force resisting the tension in the membrane is now my applied load on my frame. So this is the free body diagram of the frame. The free body diagram of the membrane would be the opposite, right? The free body diagram of the membrane, these are the reactions. So these two things are just kind of equal and opposites. This is the membrane, this is the free body diagram on the frame. So how does that work? We're ignoring the vertical component right now. We're just looking at the horizontal component. How does this work? Well, let's take a section of it. Let's take a half section. We use our method of sections. We know that if the whole thing is in equilibrium, then any component must be in equilibrium. I'm not going to draw quite so many arrows this time. We're pulling in at all of our trampoline springs. What's interesting about this is that the horizontal component of this arrow is equal and opposite to the horizontal component of that arrow. Horizontal component of this one equal and opposite to that. This one equal and opposite to that. This one is equal and opposite to that. So the sum of the forces, the sum of the horizontal applied forces equals 0. So we use the sigma, large scale, upper scale sigma, to represent the sum. The sum of the horizontal forces equals 0. So what's left? Well, we can see that this one has a small vertical component. This one has a slightly larger. This one has a slightly larger. So each one of these contributes a vertical load. And so we're held in equilibrium like this. So here we've done a section, a portion of it, held in equilibrium by vertical loads that are tangent to our ring. And that is a diagram that's in equilibrium. This is a beautiful thing because this says that the boundary of our trampoline, notwithstanding that these are very, very large forces, the boundary of our trampoline is in equilibrium with no bending on it. Which means that this is just a simple compression ring. This is a variation of what's called the boiler problem. And the boiler problem is how much force is in the wall of a boiler. We know that they call it a boiler because that was, but it's also a tank problem, right? Tanks are built in cylinders. I mean, when you're driving down the road, tanker trucks are in cylinders, right? And there's a very explicit reason why they're in cylinders. They're in cylinders because under uniform pressure, when you have something pressurized inside, that pressure can be resisted by straight axial force with no bending, which means the walls can be very thin. It's very, very efficient. Okay, Shannon's given us some really good ones. I'm going to skip the swing because I already talked about a swing. And I talked about, so this is the swing in static equilibrium. We talked about that from the swing in the tree. Here's a swing that is not in equilibrium, and we talked about that also from the tree. So I'm not going to talk about the swing, but I am going to add one thing. And we're going to talk about a tether ball. Because my kids also have a tether ball in the backyard, and this is an interesting problem. So we have a pole, we have a ball, somebody has pushed this ball, or is pushing this ball, so that even though this is a dynamic thing, we're going to represent that force with a static horizontal force. Fixed at the base. What holds it in place? We have a horizontal reaction, resistance, and a moment. So it's a simple cantilever problem. So you might be saying, but Dave, you promised me that this was an interesting problem, and that is not at all interesting. So let's talk about what makes this interesting. What makes this interesting is what's happening below here. Now we have grade. We have a thing embedded in the ground. To that, now, what is our reaction here is now our applied load. In this diagram, we have M and we have H. Hello?
Hey, you talk a lot.
I know, I'm going for it.
Was that supposed to be a half-hour video?
Yeah, I know, I leaned in. I'm making something of it. Have I been 2 hours?
You're an hour and 40 minutes almost.
Okay, well, it's good. It's all good stuff, Shannon, I promise.
I know. I know.
So what was our reactions are now our applied loads. You can see that the signs have changed. Let's see what's happening here. We're embedded in the ground. The ground will not let this pole move laterally in any way. We've also got vertical friction. We're going to ignore the friction. Again, if it helps, leave it off. If it hurts, incorporate it. So we're going to say that the soil force can only bear perpendicular to the pipe. What do we know? We know this whole pipe is going to have a tendency to rotate into some new position. So we've got rotation on this pipe. I've drawn it in the wrong spot actually, because I know about what point it rotates. But we know that somewhere up here we have a reaction this way. Somewhere down here we have a reaction this way, a horizontal reaction. Now let's look. We've got 3 horizontal forces. We know we can add them up to be 0, so that the sum of those two can be horizontal. We're applying a moment in this direction, but our reactions counter it. So we're kind of in a good place here. We know that it's going to rotate somewhere. We know that it's going to push this way on the soil at the top. It's going to push this way on the soil at the bottom. Now, how do we go about quantifying that? And we know that we're going to have some distribution of we know that the resultant of these reactions, of course, has to be here. I should have used, I'm going to call this RH1 and RH2. So the horizontal reaction 1, horizontal reaction 2. R is I'm going to use for resultant. I know my reaction, my resultant has to line up with the applied force, which those two, we're not going to talk about this today, but these two opposing forces can have a reaction that's out here. Okay, so now we'll think about how can that force be distributed. We already kind of talked about if it's a triangular, it's at the 1/3 point. If it's rectangular block, it's in the middle. If it's trapezoidal, if it's something else. What some people do is they break this into two rectangular blocks. We say, I'm going to have one rectangular block here, one rectangular block here, and solve for those stresses. And that's a reasonable approach. The bridge code has that in it. But what we also know is that right at the very surface, there's no weight on the soil, and so it has no sideways resistance. So that's one thing. We also know that at the point of rotation, you can't jump instantly from a maximum this way to a maximum that way. That can't happen. So that's an approximation. So we know that there's going to be a smooth transition of bearing force that goes from 0 here. It's going to be 0 here because there's no movement at the point of rotation, and then it'll be at some value here. So a guy named Cherniak proposed, what if it looked like this? What if that was our bearing pressure distribution? Satisfies all our constraints, right? It's 0 right at the top. It's a 0 at the point of rotation. It's a maximum at the base. So this is our bearing pressure. This is the diagram that looks like our bearing pressure distribution for embedded pipe. We don't know what the shape of that curve is, but the fact is that it doesn't matter all that much what the shape of that curve is. We know that it's a curve of some kind. And it happens that we can quite easily quantify a parabola this way plus a triangle that way equals that. So we can break it down into these two components. We can have a reaction. We can have a reaction to the resultant of the parabola pushing this way, the resultant of a triangle pushing this way. We can solve those two, the parabola being here, the triangle being here. We can solve those two for equilibrium. Once we've done that, once we know the reaction, we know the magnitude of our parabola, we know the magnitude of our triangle, once we know the resultants, from that we can determine the peak stress and the peak stress, and we can check to see if these two peak stress points exceed the capacity of the soil. So it appears to be, and it is, a very complicated problem. But as soon as we make a few very simple assumptions, the assumption being there is no force at the ground, there is no force at the point of rotation, we have a smooth transition between them, and whatever that curve is doesn't matter all that much. So we're going to use a parabola because it's easy to calculate. All of a sudden we have the ability to calculate our peak stresses on our lateral pile. So there, my good companions for today, is a whole whack of free body diagrams. It was very fun for me. I hope you enjoyed it. There's nothing like explaining something to solidify it in your own mind. So I'll look forward to meeting all of you in person at some point.
We can see your face for just a brief second if you'd like, for those who've managed to stick around.
That's right. Yeah, this is the climax. This is what it was all for. Okay.
All right.
Bye,
team.